Welcome to the office. We want to talk about the idea of a greatest common divisor. Now, for those of you that are education majors, of course, greatest common divisor is something that you'll end up talking with your students about. And you won't be talking to them about groups necessarily. Maybe you'll have some excellent students, and that might be something that you want to approach with them. But as far as a high school student goes, right, I'm assuming secondary education here, then you will end up talking about a greatest common divisor. So secondary includes middle school as well. Of course, that conversation could occur there as well. Elementary school, maybe, maybe not, right? You're just starting your multiplication, so I'm not sure where exactly that would lie. But yeah, we want to be able to talk about greatest common divisor at that level, which wouldn't be put within the context of groups. So how does it fit within the context of groups here? Well, we give a weird definition, but it's still describing the exact same thing. So if we have two positive integers, r and s, here we define the positive integer d, the generator of this cyclic group, to be the greatest common divisor of the integers r and s. We write that d is the greatest common divisor of r and s. So, I mean, that's really weird. We have some subgroup. So H is generated by linear combinations of R and S, and then whatever thing will generate all of these possibilities must be the generator for that. I mean, that just seems so weird. There's one number that can create any linear combination of R and S. That seems crazy. Oh, maybe it doesn't seem crazy to you, and that's fine. But the point is that the fact that H is cyclic has not been proven. I even flipped back a few pages as far as seemed appropriate to say, all right, did we ever say that this is cyclic? Did we establish that taking linear combinations of integers is actually cyclic? There's a one number, and you can take multiples of that to get all of what's possible in their linear combinations? That seems just, it does not seem obvious to me. Of course, after you think about it, maybe then it is, but we haven't actually established it. What is possible is, let's see here, in section, this particular section that we're discussing within our text, section 6 here, exercise 45 will verify that H is in fact a subgroup of some group. Okay, so you'll start to get this idea of, okay, yeah, H does generate a subgroup at least. That's fine. But then you want to talk about, well, how do we know that it is actually cyclic? And you might be able to use this idea or a prior knowledge of greatest common divisor to then be able to discuss what it would look like to say that that thing is the generator, but to define the generator as, or to define the greatest common divisor as the generator, then you start to get into the cyclic definition. So how can you prove it without the idea of just saying, oh, use the greatest common divisor? It seems kind of crazy. Anyway, greatest common divisor, we know what it is. The fact that this shows up in our section on cyclic groups is simply the fact that this is an application of cyclic groups. Greatest common divisor is the generator for a cyclic group. Cool. That's all that we really want to take away. In terms of computing greatest common divisors, we're not going to use this to do that. There is an algorithm for it. I don't remember if it's named after a person or not, but there is an algorithm for finding the greatest common divisor of two numbers. I'm not expecting us to find that. What we can do is we can consider the prime factorizations of these numbers. If you know them off the top of your head, that's fine. I don't. But I do know that 60 is, I can write it as 6 times 10. 6 times 10, that's the easy one. 6 is 2 times 3. 10 is 5 times 2, so I can recognize this as 2 squared times 3 times 5. So 2 squared there, that didn't look very good. And then 48, that one I'm pretty familiar with as 4 times 12. If you only observed that it was even, then sure, 2 times 24, that's fine. But 12 can be written as, well, I suppose 4 can be written as 2 times 2, and 12 can be written as 4 times 3, which is 2 times 2 times 3. So that's 2 to the 4th times 3. So what is their greatest common divisor? Well, the greatest common divisor is the factors that they have in common. The GCD is made of, I don't know the best way to say that, but how do we create the greatest common divisor? It's made up of the factors in common to the prime factorizations. Now that only works if you have numbers that are relatively small, right? And in the hundreds for the most part wouldn't be too bad, but they're relatively small for you to be able to create the prime factorizations of, okay? In this case, they have two factors of 2 in common. So the greatest common divisor of 60 and 48. There's 2 factors of 2 in common. There's a factor of 3 in common. There's no more factors of 3, and this one doesn't have a 5. So that's it. 2 times 2 is 4. 4 times 3 is 12. So 12 is the greatest common divisor of 60 and 48. As simple as that. All right. That's all that I wanted to share for this video. So join me for more properties on cyclic groups here in the office.